Hello, everyone. I'm Ethan from Indiana University, Bloomington. This is a joint work with Institute of Information Engineering, Chinese Academy of Sciences. Today, I'm glad to share with you guys our new work. We provide you a new technique to automatically discover cellular network vulnerabilities just by analyzing its documentation. First, let's look at a cellular network. With new technologies emerging every generation, the cellular network has profoundly changed our life, especially the 4G, with a higher rate, faster speed, and greater capability, allowed us to connect our work and daily life to just one small mobile. That really brought us an intelligent life. The cellular network plays a pivotal role in the current world. So naturally, their security and privacy become critically important and are expected to be thoroughly scrutinized. But unfortunately, actually, today the cellular network are much less protective than thought. It often involves various security and privacy risks. And most vulnerabilities are discovered by ad hoc manual analysis. Of course, recently, there are some systematic solutions. They utilize the traditional software vulnerability discovery methodologies, such as fuzzing and mode checking into the cellular network. But they still cost a lot of manual effort. In fuzzing, previous work manually identify the security properties and use them to guide the mutation of the injected messages. This requires a human to have an in-depth understanding about the network design. In the model checking, previous research even rely on more manual effort. People need to build a model manually and further give the security properties manually too. So considering current situation, we want to explore a both systematic and automatic way that can discover the cellular network vulnerability. Looking into the cellular network development ecosystem, we found a specific phenomenon. The cellular network connects all over the world. It is a super complex system, including many different kinds of devices such as mobile, LTE device, base station, core network, and so on. So natural, there are many device manufacturers from all over the world. So in order to achieve the cellular network, all the manufacturers must follow the same specification, which is provided by 3GPP, an organization uniting telecommunication standard development organizations across the world and providing and maintaining cellular telecommunication technology specifications. Because of the complexity of the cellular network, now 3GPP has more than 3,000 specifications for it. We randomly checked several of them. All of them are pretty long, including hundreds, even thousands of pages. We believe that such huge specifications must include some clues that can guide us analyze the network security. So in our research, we made a first step to consider one situation. When a specification describes a sensitive operation, such as transmitting a private information or releasing a connection, because of the huge number and complexity of the specification, we're curious about whether the manufacturer developers could implement it correctly and securely. If not, there may be a risk in a cellular network. In our research, we focus on the NAS protocol. Generally, we could simplify a cellular network architecture as the slide shows. When the mobile, also called UE, user equipment, want to get a service from the core network, it will connect to a base station, and then the base station connects to a core network. The NAS protocol is a layer between the UE and the enemy, which is serving the core network. The NAS provides several procedures for mobility and security control when the UE using the network. For example, in order to manage a UE's mobility, there's a attach procedure. It is used to build a connection to a network from the UE. And there's the detach procedure that is used to release the connection. And when the UE is in an idle state and the MME has information to center it, the NS provides a paging procedure. For security control, the NS also provides several procedures, for example, the identification procedure. that is used for the enemy to request a user's identity. Considering our previously imagined situation, we defined the sentence related to a sensitive operation in the NIS specification. If the network receives a detached request message before the ongoing identification procedure has been completed, the network shall abort the identification procedure and shall progress the detached procedure. Here, to abort the identification procedure could be considered as a risk operation. So we want to know when the victim UE and the network is performing an identification procedure. During this period, if the network receives a detached request message from the malicious UE who spoofs the victim UE with its identity, we're curious about whether the enemy will successfully remember to authenticate a malicious UE or just follows a short description to perform the risk operation to abort the identification procedure with the victim UE. So carrying this out, we tested in a 4G simulation environment because considering the ethics, we cannot perform experiments in commercial network. So we tested in a simulator. But in our testing environment, we surprisingly found that enemy not only aborted the identification procedure, but further released a connection with the victim UE. The victim UE finally got a DOS attack. So from this observation in the NAS, we have a new idea to find senior network vulnerability systematically and automatically. Our high-level idea is first to detect an indicator from a documentation, the hazard indicator, which describes a risk operation. And then we use it to guide the test case generation. Based on the indicator's information, we decide what attack messages shall be sent at what target state. Finally, we execute a test case in our test environment and identify the POC. So next, I will introduce the key techniques in the 3 states. First, the hazard indicator detection. As the example shows, the hazard indicator is a short description documenting operation which we consider to be risky. So it also describes a condition to trigger the operation. So to find such indicator, our approach is designed to search all the conditional sentence that implies a risk operation in the whole specification. The conditional sentence is easy to identify just by the keywords such as if, when, and extra. So the challenge here comes to how to decide whether the consequential sentence implies a risk operation. In our work, we leverage an NLP technique called textual entailment. It can decide whether a hypothesis entails a premise systematically. Here, for the example in the slide, through the textual entailment, we can detect the consequential sentence underlined in the red implies the risk operation abort procedure. Notably, the textual entailment is a model that can understand semantics. So no matter the sentence syntax changes, such as changing to a procedure shall be aborted, or the sentence uses synonyms such as using a terminated procedure, the textual entailment model always works. So given the risk operation abort procedure, we don't need to find its variations, and we can easily identify those sentences implying the risk operation while using the NLP technique textual entailment. Of course, we believe that except for the risk operation abort procedure, there are other risk operation in the specification. We also need to extract them. Here, our idea is based on observation that the risk operation will always appear together in the documentation. So we use correlation analysis, point-wise mutation information, a standard approach in computational linguistics to identify them. From the seed abort procedure, our approach extended several new risk operation description, such as release resource, deactivate context, and progress procedure. Here, the progress procedure is interesting because it is opposite to abort procedure semantics, but it does implicitly imply that when someone progresses a new procedure, he may stop an old procedure. Next, let's move to a second step. For a given general threat model, like here, a malicious UE issue sent an attack message to enemy to interrupt the communication between the enemy and the victim UE. We could have a test case template in advance. In our work to generate a test case, our approach is to automatically extract a target state and a tag message from the hazard indicator to fill the template. Here, we utilize an NLP technique called dependency passing to analyze the syntactic structure of the sentence. As shown in the slide, in the dependency passing, the verb takes the central control in the clause. All other words either directly or indirectly modifies the verb. For example, the word network is a verb's receive subject. The word message colored in red, colored in green, is an object of the verb receive. And the word detach request colored in blue has a compound relation to a word message. So from these relationships, we can identify that the detach request message is a tag message issued by the malicious UE. By the same way, we can decide the enemy is at a tagged state after he sends out the identify request message before he receives the identify response. Finally, we execute the test case in our test environment with 3 popular 4G simulators automatically. In order to achieve it, we modify the open source simulator to set hooks and run the listener on each of them. We activate the hooks dynamically according to a test case. So in the testing, when the enemy enters the target state, the hook will notify the malicious UE to issue the attack message. One challenge here is how to guide the enemy to attack the state. After analyzing, we found that most procedure states can be entered naturally after just rebooting the phone. And for the others, although they usually happen undetermined, but they are always being after the attach procedure finishes, such as the paging procedure, tracking error procedure. So we leverage hooks again. When the enemy finishes the attach procedure, we use a hook to notify the enemy or the victim UE to start the related procedure immediately to enter the target state. And finally, we check the traffic log to monitor whether the victim UE has been disrupted. If yes, we output a test case as an identified POC. Now let's look at our whole approach. In one word, we identify the indicator from the specification and then use it to guide the test case generation and execute the test case to identify the POC. Our system's input are the senior network documentation and the threat model, specifically a risk operation description as a seed that are used to extend the other risk operation descriptions, and a test case template that is used to generate test case. And the output is an identified POC. The whole workflow is automatic. Running our system on S protocol, which includes more than 500 pages and 220,000 words, we found 7 vulnerabilities in the Open 5G simulator and 10 vulnerabilities in the SSLTE and Open Air interface, respectively. All of them are new vulnerabilities. One may ask whether these vulnerabilities can be exploited in the real world, since generally in senior network, it is hard to monitor the enemy state. Here, our answer is yes. We figure out a practical attack exploiting these vulnerabilities. We don't monitor the enemy's precise state. We estimate the attack window that the enemy state may enter into. In senior network, the pager message is a broadcast message that every mobile can receive covered by a space station. Receiving the page message with different parameters, a UE will start a different procedure immediately. So leveraging it using the downlink message sweeper, attacker can identify the victim UE's target procedure from the page message and its parameters. Once the attacker sniffs the pager, he can send a tag message according to a pager's parameter immediately to perform a DOS attack. Because we cannot perform attacks on the commercial network due to ethics, we reported them to a CNVD and CNVD, to Chinese national vulnerability databases. Both of them have confirmed that the vulnerabilities indeed exist in major commercial carriers. By the way, we record our attack demo and put them in our website. If you are interested, you could watch it through this link. Under our workflow, we also tested another classic threat model. And that when a victim connects a fake network, in this given threat model, we also find many vulnerabilities and receive the confirmation from the mobile manufacturers. Finally, let's summarize our contribution. First, we provided a new technique to discover senior network vulnerabilities. We extracted the indicators from the documentation and use them to guide the vulnerability discovery. Second, we implement our approach and found 42 vulnerabilities in the real world, including 10 new ones. In our research, we proposed a new direction to discover senior network vulnerability from analysis documentation. But it is relatively preliminary, just scratch the surface. The huge specification contains a lot of other clues about the security risks. Automatic discovery of this security weakness will contribute to the great evaluation of the senior security. We will study them in our future work. And we also hope more researchers come to study this area together. That's our report. Thanks for your listening.